Okay, in this last section of Chapter 6, we're going to take a look at growth again. But in this case, we're going to look at a more realistic representation of growth, and that's something called logistic growth. And you can see right away in this picture here on this title slide, exponential growth just keeps on going and going and going forever and not stopping. And of course, in the real world, there aren't many things that kind of just keep growing without ever stopping. And you can see for this logistic growth graph, it kind of starts leveling out as it approaches some, I guess, maximum value here. I guess in the picture that would be about 1,500 for this population size. But we'll talk about the details of logistic growth as we go through this lesson. So let's recall that from the last section that we studied, some population models show exponential growth, where the rate of change of some population is proportional, and that was the key word, to the population at some time. We started off with this differential equation. We went through the steps of solving that differential equation, and then we found the solution to that differential equation, that particular solution that we ended up using in all the problems, so we didn't have to actually do the calculus every single time. So there's a kind of a problem to this model. In biology, or in biological populations, they don't increase forever. In most real populations, food, living space, disease, and many other factors become important as conditions become more crowded. Sooner or later, any exponentially growing population reaches some limiting factor, which we call the carrying capacity, symbolized by the capital letter M. So a more realistic model is this thing we call logistic growth, where the growth rate is proportional both to the amount present and the carrying capacity that remains. And of course, if we wanted to know how much space we had left, we would have to take that M, which is our carrying capacity, the most we could have, and we would subtract away the population at some time. So this is how the logistical differential equation looks. It looks almost identical to our exponential model, except instead of times p, now we're instead of times just a p, now we're multiplying by that difference between the carrying capacity and the population at some point. So you saw in the first slide kind of two graphs in one. The exponential growth graph looks like that, and now this logistic growth graph starts tapering off at some point, starts leveling off as you get closer and closer to whatever the environment can sustain for a certain population. That is what we call a carrying capacity. It's the limiting factor, or the maximum sustainable population. So unlike 6.4, where we actually solve the differential equation for exponential growth up here, we're not going to go through all those steps for the logistical differential equation. I'm just going to go ahead and kind of give it to you here, and that's what we're going to use when we need it to solve certain logistical growth model problems. So one of the common examples to kind of start off the logistical growth discussion usually revolves around the spreading of a rumor. So imagine the scenario where you just heard a rumor at school that math is fun. A shocking rumor, I know, but we all know that's true. So let's imagine that scenario. Rumors spread like wildfire, but more correctly we can describe that growth as logistical. Only a certain number of people can ever know this rumor, so of course it's not going to just grow forever. So let's take a look at this graph. This is a logistical growth graph where I'm plotting the amount of students that know the rumor on our y-axis and the time it takes to hear that rumor on our x-axis. So we want to spread the rumor to all 2,000 students at our school. So that is our carrying capacity. No more than 2,000 students can hear this rumor, so that's the most that this graph could ever hope to reach to. So you'll notice, based on this graph, the rumor starts to spread slowly. The slope of this graph is fairly horizontal to begin with, and it starts getting steeper and steeper and steeper as time goes on. The more that know the rumor, the more people there are to help continue spreading the rumor. This is the strictly exponential growth part of this graph. But at some point, things are going to change. And this point is going to be kind of just pointed out here. It's a random point on our graph, so to speak, just to talk about what a point on this graph would represent. Below that graph, or the value below that graph, would be the students who have heard the rumor. And that makes sense. At first, it starts off with not so many students, but as time goes on, more and more students hear the rumor. So what is the distance between the carrying capacity and that point represent? Well, that represents the students who have not heard the rumor. Of course, m minus p. So hopefully that graph, or this graph, now makes a little more sense in terms of any point along the graph. Below any point in the graph, at least in this particular situation, are the students who have heard the rumor. And the distance above the graph from the point to the carrying capacity are the students who have not heard the rumor. I was mentioning something a little bit earlier. This point that we have here is just some random point, but there's a very important point on this graph, and that's right there. There is a point of inflection on these logistical graphs. And you might notice, to the left of this point, our graph is concave up. To the right of this point, our graph is concave down. So that, of course, means there's a point of inflection. That always happens, and this is the key, that always happens at half our carrying capacity, or m over 2. And of course, in this case, that would be 1,000. That's what we call the point where the growth is the quickest. The rate of quickest growth always happens at the point of inflection, or at half of the carrying capacity. So as more and more students find out this rumor, there will be fewer and fewer students who haven't heard. So the rumor can't continue to spread at the same rate. At some point, that rate's got to start slowing down. And that's the key to this second half of the graph, I suppose, this piece to the right of our point of inflection. This piece to the right of the point of inflection can be described this way. The rumors continue to spread, but at a decreasing rate. Quite often we refer to this part of the graph as increasing at a decreasing rate. We still have an increasing function, of course, but it's at a decreasing rate. It's not the same rate as to the left of the point of inflection. So that's very important. Every once in a while, you'll see a problem worded that way, where it wants you to identify the portion of a logistical graph that's increasing at a decreasing rate, and now you know that's the point, or that's the interval to the right of our point of inflection. Okay, so hopefully that little example and the use of this graph and the pieces of the graph kind of demonstrate the things or the ideas we need to know about logistical growth. Couple last little follow-up items that are very important concerning possible questions you could be asked. What if a question was posed to you to find the limit as t approaches infinity, or as this graph keeps on going to the right, of p of t? And keep in mind, this graph here in red is our graph p of t. Well, what is that limit approaching? What is the graph approaching as we keep on moving to the right? Well, it's going to eventually approach our carrying capacity. Remember, a limit is a y value, and as this graph keeps on moving to the right, it's eventually going to hit that carrying capacity of m. Another frequent question that will come up from time to time, I suppose, I'm not sure how frequent it is, but definitely from time to time. What if you were asked to find the limit of this logistical growth equation, but of the derivative? Here we're being asked to find the limit as t approaches infinity of the derivative of p. Well, this graph is still very helpful. You just need to take into account that this p prime is talking about the slope of the graph. What is happening as this graph keeps on moving to the right concerning the slope? Well, you'll notice that graph is kind of leveling out, and it's getting flatter and flatter and flatter. So the slope of that graph is approaching a slope of 0. So the limit of the derivative of this graph as t approaches infinity would be equal to 0 because the slope is eventually leveling off to become 0 as we approach that carrying capacity. Okay, so let's take a look at a very detailed example involving logistical growth and all the math involved. So I'm going to keep that theme of a rumor here to kind of take us through this example. At this high school, Riverdale High, there are 1,000 students. A rumor is spreading through the school where the rate of change of the people, P, who know the rumor is proportional, and that's the key word, to the number who know the rumor and those who do not after T days. On the first day, or actually on day 0 times 0, 4 people and 16 of their friends start a rumor, which is spreading logistically. And technically we don't even need that word. We know it's logistical because the most, or the maximum amount of people that can even know the rumor is 1,000. A day later, 50 students know the rumor. How many students know the rumor after 10 days? Okay, so to figure this out, we need our logistical growth model equation so that we can plug in the time of 10 and answer this question. So that's what our task is. Set up a logistic growth model equation, also graph that equation, and then as a follow-up question, find when the rumor is spreading the fastest. And just keep in mind from that last slide, the rate of quickest growth concerning these logistic growth model equations is at that point of inflection, which is half of the carrying capacity. But they're not asking us for the population when the rumor is spreading the fastest. That would be easy, that would be 500. They're asking us to find when the rumor is spreading the fastest. So we need to find the time when the population is 500. And again, the only way to do that is to get our logistic growth model equation. So let's go ahead and start. That's our logistic growth model equation. Again, a lot more complicated than our exponential growth model equation, but it's there so we can start using that equation. So we can at least get something out of the way real quick. We know from up above that this school has 1,000 students. So our carrying capacity would be 1,000 students. So we can plug in 1,000 into the top of the fraction, and then also take note that the carrying capacity M is also in the power in the bottom for the base E. Okay, so the first thing we have to find is that value of C. To find the value of C, we can use what we know in terms of this story at the beginning of it. At time 0, the population that knows the rumor is 20. The 4 people that started it, and the 16 friends that also happen to know it. So we can go ahead and take that value and plug it in. We can set the equation equal to 20, and for time, we can plug in 0. Okay, so of course we know e to the 0 is 1, so we're just left with 1,000 over 1 plus c equals 20. Didn't really have the space to show maybe the tiny steps here, but realize we could take these two values and switch them. And I guess the details here that involve and why we can switch them are that we can take this 1 plus c as one unit and multiply it to the other side, and at the same time divide the 20 over to the other side to, of course, get 1 plus c is equal to 50. Of course, if we subtract the 1 to the other side, we'll get a c value of 49. So kind of just keep that in mind. Okay, now that we know what the c value is, we can plug it in, and now our logistic growth model looks like this below. It's still not quite complete because we need that k value, but we're getting closer to that step. So how are we going to find the value of k? Well, they give us one other piece of information. They say after 1 day, 50 students know the rumor. So we can use that data point just like we did with our exponential growth model equations and use that to find k. So if we plug in 1 for time and set our equation equal to 50, we can now solve this equation for k. And just like that last example you saw, we can take these two and switch them. We can switch them because we can take the denominator and multiply it to the other side, and at the same time divide the 50 to the other side with the 1,000. And that, of course, would give us 20. A couple steps in one that I'm going to have to do here. We can subtract 1, which would be 19, and then divide by 49. And now we're ready to find k. Like you saw in that last section with exponential growth, if you have a k trapped in the power of e, we need to take the natural log of both sides. Once we do that, we can divide by the coefficient in front of k, which is a -1,000 here, and while that k does not look very nice, that is our exact k value here. And just keep in mind, you don't have to put parentheses here, but just to emphasize what's going on, that 19 over 49 is inside that natural log function. Okay, now that we know c, and we plug that in, now that we know k, we can certainly plug that in and get our logistic growth model equation. Luckily, there's a little bit of simplification that can happen here. Those negative thousands will cancel each other out nicely, and then we're left with this as our final logistic growth model equation. And again, just be careful here. It's not required, but it'll help emphasize what's going on. That 19 over 49 is inside that natural log, and then we're multiplying by t. So be very careful with those orders of operations there. Okay, so now we can go back and answer the original question that was posed. How many students know the rumor after 10 days? Well, we can take 10 and plug it into our equation. Before we do that though, if we take a look at what this graph looks like, you should certainly pause here and see if you can get your TI-89 to give you the same exact graph. You'll be doing a couple problems like this, and it's going to be helpful if you kind of sort out your issues you might have typing this into the calculator before you try those problems. So just kind of take note. When you graph this, I would not graph the entire window, so to speak, that your calculator will give you. You should restrict that window to just the first quadrant, and that's what you see right here. This is our origin right here at 0, and then I went ahead and made the scale, as you can see, on the y-axis 100. Each of those little marks there is 100, so that'll make it look a little bit nicer if you do that. The other thing I did is on the x-axis, I made the maximum value 10, just to get enough of the picture here to kind of see what's going on. So again, if you want to pause and make sure you can get this picture in your calculator, that was probably a good idea. Okay, but now we can answer, again, the question that was posed to us. How many students know the rumor after 10 days? Well, that's just a matter of plugging in 10 into our logistic growth model equation. Again, definitely pause here. There's a lot of stuff to try to type in your calculator here, and depending on your ability level, that could either go good or bad. So you might want to try to pause and see if you're going to get the answer that's going to come up here. If everything goes well in your calculator and you can type all this out, you should find that after 10 days, 996 students know the rumor. So definitely important to know, and that's actually why I set my x-axis maximum value to 10. Since 1,000 students are going to be the maximum number that could even know the rumor, well, we're pretty much there after the 10 days. 996 students know the rumor after 10 days. So that's pretty much the max it's ever going to get to. So that's why I made my x-axis go from 0 to 10. But now we can answer a follow-up question. When is the rumor spreading the fastest? And this is where your calculator skills are going to come in handy. We know that this logistic growth model equation is growing the fastest. The rate of quickest growth happens at half of your carrying capacity, which again in this case is going to be 500. So I'm going to go back to the y equals screen and graph the line of 500. Y equals 500. The reason we need to do that is because we're going to use the calculator to find that intersection point right there, because that's the time, or the x coordinate at that point is the time where the rumor, or when the rumor is spreading the fastest. So if you kind of already know how to do this from the practice we've had, great, but here you'll see some animations of the steps you'll need to take to find the intersection between those two graphs. So you'll need to go to F5, which is intersection, It's going to ask you to identify the first curve, and it's going to choose the logistic growth curve, so just press enter there. It's going to ask you for the second curve. The second curve, of course, is the line y equals 500. And then it's going to ask for a lower bound, which means put the cursor just to the left of the intersection point and press enter. The upper bound will be a point just to the right of the intersection point, press enter, and then it gives us that intersection. Of course, the y coordinate is 500, which we already knew, but the key here is we were looking for the time when the rumor is spreading the fastest, and it turns out that happens at 4.108 days. Okay, so in that last slide we did a really big and involved problem, but usually on the AP test, these logistic growth model equations are a little more straightforward and you don't have to quite go through all that process. So here we're given a differential equation, but it doesn't mention its logistic growth. We're going to kind of have to recognize that it's logistic growth, and we'll get to that in a second. This differential equation has a solution curve of y equals f of x, and it contains the point 0, 1/4, and we want to find what the limit of that function is as x approaches infinity. So what you're going to have to remember from the slide where we first started talking about logistic growth, when I introduced that problem where a rumor is spreading that math is fun, that's just another way of asking you to find the carrying capacity. Remember, if we were to actually solve this differential equation, that would give us the original function, which is f of x. And if we're asking to find the limit as x goes to infinity of that function, that's just, again, another way of asking us to find the carrying capacity. So the key for making this problem to work is to get our differential equation, which we have here, to be in the form of the logistic growth model differential equation, which we have here. And you'll notice the key for this logistical growth model differential equation is that we have some number m minus our independent variable, which in this case is p, but for our particular problem here, it's y. So you'll notice, to get this to work out, since both of these terms have a y in them, we can factor that y out. So let's go ahead and factor that y out. But on top of that, we can't have a number in front of our independent variable here. It just has to be a number minus p, or in this case, a number minus y, which means we need to factor out a 2y. And that might be a little counterintuitive because there is no number 2 in this term. So how are we going to factor out that factor of 2 from the y when it doesn't exist there? Well, the way it's going to work is that we kind of have to think backwards in a way. What number times 2 would give us that 1y? And it turns out that would be 1/2. And of course, when we factor out 2y from the second term, we're left with just y. So, is this actually the correct factoring? Well, always go back and check. If we were to take that 2y and distribute it, 2y times 1/2 is y, 2y times negative y is negative 2y squared. So it definitely checks out. So whenever you're factoring these logistical growth model differential equations to get it to look in its proper form, always double check and make sure you factored it correctly because of these little factoring issues that might come up. But either way, once we do that, we're ready to go. You can see that k is equal to 2. We're not really concerned with that in this problem, but we know k is equal to 2, and now we know the most important thing we're getting after in this problem. M is equal to 1/2. And if m is equal to 1/2, that's our carrying capacity. And if our carrying capacity is 1/2, then we know that the limit as x approaches infinity of f of x is equal to 1/2, because again, that's our carrying capacity. Turns out also, just as a little bit of side information, that initial value they gave us, that point, was just some unnecessary information. Always kind of a good thing to look out for from time to time, as some problems will give you extra info that you don't need. Okay, one more example. We have the rate of change in number of coyotes in a population that's given by this differential equation here. C is the number of thousands of coyotes T years after January 1st, 2000. For what values of C is the number of coyotes increasing the fastest? So here you're going to have to recall from the last slide when we did this in the example, and then 2 slides ago when we first talked about it. We know the rate of quickest growth is at half of the inflection point, is at the inflection point, which is half of the carrying capacity. So that's really the key. Can we identify the carrying capacity in our logistic growth differential equation? Well, again, we kind of have a dilemma, so to speak, here. This logistical growth differential equation is not written in its proper form, so to speak, where we want Kp times m minus p, or in this case, the p is a c, a capital C. So just like the last problem, but this one's a little bit easier, we need to factor out a c from both of the terms, but luckily the constant is kind of easier to identify here. Both of these terms have a factor of 3 in them, so we can factor out a 3c. If we factor out a 3c, we'll be left with 3 minus c, and now that matches our logistical growth model form, where it's Kp times m minus p. And again, just like you heard me say before, you might always want to check and make sure you factored correctly, since these problems are very short and simple in a manner of speaking, and you don't want to make a silly factoring error. Okay, now that we have this in its proper form, do we know what the carrying capacity is? Well, yes, the number minus p, or in this case, the 3 minus c, indicates what our carrying capacity is. Our carrying capacity in this problem is 3. So if we want to find for what values of c is the number of coyotes increasing the fastest, we know that happens at half of our carrying capacity, which is 3 over 2, or 1.5. So at c equals 1.5, the number of coyotes is increasing the fastest.